Here we're going to look at the area properties of definite integrals. So for this video to work for you, you need to understand what an integral is, have a basic understanding of calculus, and be able to do definite integration. And in this video we're going to link back to the fundamental theorem of calculus. Okay, so this video is not an introduction to the fundamental theorem of calculus. We're going to link back to it. We look at some area theorems or summary of results related to area theorems. We will look at the idea of algebraic area. That's algebraic area under a curve and physical area. So they're the things that we'll cover. There will be a video number 2 which will look at things such as areas between two curves and areas bounded by lines and curves. That will come after this video. So the fundamental theorem of calculus can be written as such. So that's the integral of f of x dx, some function between limits a and b, is the definite integral with the limits upper limit and the lower limit subbed in and subtracted. So the capital F is the primitive or the integral, and thus we've seen this in some of our work and some of our calculations. So it's important to remember the capital F is the primitive, or it is the integral. It happens after integration has occurred, so don't get the uppercase and the lowercase f's mixed up. As you know, you get some real number as a result. So the result is a definite real number. It's a numerical result, not a function. Okay. And no, it's not factorial, by the way, that's just exclamation mark. Now let's look at what's called the algebraic area. So, algebraic area, what does that mean? So we're talking about areas that are bounded by a curve, which we call f of x, also the x-axis, and ordinates a and b, so they're vertical ordinates or vertical lines. Okay, so we have a curve like this one over here. We have an f of x, we have an x-axis, and we have an ordinate line on each side. And you can see in the first one there's a purple area there. An algebraic area is called that because it will have a positive or negative sign depending on whether it is, well, one of the things is whether it's above or below the x-axis. That's the main thing. We're going to look at, initially we're going to look at 4 types. So type 1 there in the purple. So let's cordon all this off. And that one there refers to diagram 1. And so we have in diagram 1, we have the condition where a is less than b. We have the condition that f of x is greater than or equal to 0 at all times over that interval. And so what happens when we take the integral of the function between b and a, we get a positive number as our result. So the area is positive. The algebraic area is a positive quantity. In the second one, a is less than b again, but f of x is always less than or equal to 0 at all stages in the interval. So what happens when we take the integral of f of x dx? We get a negative answer, a negative value, or a negative algebraic area. Now in the next one, we have a look, if you look closely, the limits have been swapped around so that in number 3 we have a is now greater than b, okay, and that's different. So what we've done is we've reversed the limits around essentially, and the graph is still above. So you notice how in graph 1, when a was less than b and when the graph was above, we got a positive answer, okay, but in this one we'll have a negative result. So it's like a reversal of the limits, and the result comes out as negative. So it's the opposite to that first one, even though the area is above the x-axis. Same with this last one here. It's the reverse of number 2, where we had a negative outcome, because a, again, these have been swapped around. We're still integrating in the same manner, but we've swapped the limits around and such that a is greater than b, and that will make a positive result. Another similar result occurs when we compare the purple graph and the green there. And what have we done? Well, a is smaller than b in both, and f of x is above the x-axis in both. But this one's called reversal of limits, because if you look at the summation symbol there, the limits have been swapped around. So that one's called reversal of limits. And have a look, you can tell what's going to happen here, because understandably you get that calculation occurring, and so that will mean negative of the green one. So what I'm doing, this is the green one I'm rewriting, will equal the purple one, which is what I'm writing now. So it's an interesting result, and you can try that yourself. So swap the limits of integration around, you get the negative of what you started with. The next one is the last one of these little results, is continuous interval is one way you could title this one. And basically we can break these down. If we wanted the integral from c to a of f of x, if it's convenient, we do have the option of breaking it down. You can see there's a green zone and a purple zone. The curve is always above the x-axis, so it's a fairly straightforward case. And what we can do is integrate from c to b of the function, and then add on the integral from b back to a, which is the purple section, and add them together to get the same result. So that's if the interval is continuous. Now importantly, what happens if we've got this case here where some of the interval is above and some of it is below, and we haven't looked at that yet? And if we needed to take the integral of f of x between c and a, well, it depends if we're looking at physical area or the algebraic area. So there'll be two different answers for this particular scenario that you see. Essentially, physical areas are always considered to be positive, regardless of whether they are above or below the x-axis, whereas algebraic areas have signs on them. So the sign of that will be negative because it's below the x-axis, and the sign of that one will be positive because it's above the x-axis. And you'd see that just by inspection, it's likely that you would get a negative answer overall because the green essentially outstrips the purple, and the green is negative, so you get a negative. However, physical, you'd have to take the absolute value of the area of A2 and then add it to A1 to get the total area. Now, if in doubt, if it doesn't say, assume algebraic area. If it's a physical question, you might not be able to assume that quite so easily. So if it's a problem-solving worded, real life type situation, you will need to be careful about the assumption. But if it's just an abstract question that doesn't say, you can assume that it's algebraic. It certainly makes a difference. Let's look at this one here. You can see that if we take the integral of x cubed between -3 and 3, there'll be a big difference between whether we're taking the algebraic or the physical area. So let's do algebraic first. And we just simply take the indefinite integral. We get 0 as our answer, and looking at it by inspection and understanding, if you understand the shape of x cubed, that should make sense. So for the physical area, we have to break it into two parts. You need to, either with your graphics calculator or analytically, need to work out where the intervals are such that the graph is above and below the x-axis. So on this one, it's pretty easy. We can see that it's between 0 and 3, that interval of x. You've got a straightforward definite integral there. For the section that's between -3, x equals -3 and 0, we have to take the absolute value there. Can you see the absolute value symbol? So that's because that interval will come out as negative, okay, when we use definite integration, and the absolute value will essentially remove that, so it treats it essentially as a positive. So basically we got this here, plus that there, and so that will be 81 on 4 minus 0 plus the absolute value of 0 minus 81 on 4, because -3 to the power 4, it comes out as a positive. And we got 81 on 4 plus the absolute value of 81 on 4, and that's 162 on 4 because the negative gets treated as a positive, and that's 40.5 units squared. If you got to put the units on, I suppose, if it's a physical area. Let's do one final one with just an algebraic area that's a little bit different. So let's just do this one, as I said, only as an algebraic. If you looked at, you would get 8 units if it was physical, 8 units squared if it were physical. So let's compare that to what we get here. And if it were physical, we would have to actually treat these intervals above and below separately. But look at what happens with the algebraic. You can just put it straight in, and you see that we don't have to split it up. It takes care of that automatically. So we integrate and we get the expression you can see there between 4 and 0, so we sub those values in. Okay, so speeding that up a bit, we get 5 1/3 units squared. Pause the video to have a look at the calculations. Interestingly enough, if we go back to one of those earlier theorems, we could have broken this up. You can see that that's between 0 and 4. We could have broken that up according to the two naturally occurring intervals here, and there's one between 0 and 2, and then another one between 4 and 2, and we could have integrated the function between 4 and 2 and added that on to the integral between 2 and 0 of the function above. Dx, and interestingly enough, those two results respectively would have been negative 1 1/3 and 6 2/3. You can see the 6 2/3 there and the negative 1 1/3 there, if we're talking about algebraic area. And you can see that when we add those together, that will be 5 1/3, which matches our answer.